Hello, everyone. Welcome to the temporal graph reading group on January 25th. And today we are very excited to have Hongkuan, who will be presenting his work, DistTGL, distributed memory-based temporal graph neural network training. Just for a little bit of speaker introduction, so Hongkuan Zhou is a PhD student at Mason Department of Electrical and Computer Engineering at University of Southern California. His research interest lies in the acceleration and application of GNNs and temporal GNNs on general purpose hardware. And I will leave the mic to you to get started.
Yes, thanks for the introduction, Andy. So, hello everyone. I'm Hongkuan. Today I'm going to present our work. So this is the work published in Supercomputing 23, and it was performed during an internship at the AWS AI Lab, the DGL team. And it's a joint work with my colleagues Da Xiang and George from the DGL team, and also my advisor, Professor Victor Pasana. Okay, so let's get started. So I'll arrange today's presentation as follows. So I'll start with some background in temporal GNNs and memory-based temporal GNNs, and what are the challenges to scale them to large-scale industry-scale graphs. And then I'm going to introduce our approach, DistTGL. So DistTGL mainly have three improvements over the existing solutions. So the first one is a more capable model. So we enhance the existing model with the static node memory. And the second is the more efficient training algorithm. So to compensate the accuracy loss when you use the large batch size, which I will discuss in detail later. Besides the straightforward mini-batch parallelism strategy, we propose two additional parallelization strategy, which is called epoch parallelism and memory parallelism. And we also provide heuristic guidelines for the DistTGL user to achieve the optimal training configuration that combines all three kinds of parallelism based on the characteristics of the dataset as well as the hardware that you are using. And lastly, we identify that the mini-batch generation, the mini-batch generating is the major overhead in previous works of multi-GPU TGN training. So we propose an optimized system which achieves zero mini-batch generation overhead up to 32 GPUs on 4 machines. And lastly, I'm going to show some experiment results and conclude today's talk. So let's start with the background. So since this is a temporal GNN reading group, so you guys should be pretty familiar with that. So I'm just going to quickly go through it. So the goal of this temporal graph representation learning. So in this work, we focus in the continuous time dynamic graph. So that is to embed nodes in continuous time dynamic graphs into low dimensional vectors. So for example, on this on this left figure, we have a temporal graph, and at the time t0, we can have an embedding vector of this node v0. And on the right side, at another time t1, the graphs change, so our embedding also changes. And this embedding can be used in many real-world applications, for example, the fraud detection and event prediction. So there are many different ways to do this temporal graph learning, and temporal graph representation learning. But recently, there is one type of model which we call the memory-based temporal graph neural networks that achieve a very good balance between the accuracy and the training time. So the intuition of memory-based temporal GNNs are pretty simple. Is that you have a dynamic graph, and there are more and more incoming edges as time evolves. So your neighbor or your history neighbor of a node, the size will grow pretty fast. And if you sample a fixed amount of supporting neighbors in the when you compute your GN, for a given node, then as time evolves, you will not be able to recover enough information because your neighbor list is just being longer and longer. And the solution here is that for each node, we want to maintain a node memory which captures the node history, especially the long time history, to aid the GN aggregator, which is more responsible in capturing the recent events or the recent history of the node, so that we are able to capture the entire information in the dynamic graph. And node memory is typically maintained by GRU cells. So if there is an interaction between node U and node V at time t, what we do is that we first generate a message vector. So this message vector is a concatenation of the node memory, current node memory of the source and the destination node, time encoding, and also the edge feature. So we use this message vector to and a GRU cell to update the node memory of both node U and V. And later we just apply a standard QKV attention to gather the to compute the information, compute the output node embedding using the most recent neighbors of a node. So note that there's a problem. Everything looks good except that this node memory update process is serial. So if you have two events that happens on a node at two different times, before you start working on the second one, you will have to make sure your first one is updated because your SU of the second event obviously depend on the SU of the first event. And another thing is that temporal GNs currently are usually self-supervised by the temporal edges, which means your training task is to identify positive edges from negative edges. So combining these two things, it's actually brought some issues in the data parallelism. So in order to in order to train temporal GNs in batch, and that is the only way to train it efficiently, what existing works do is that they process these graph events in batches and ignore the intra-batch dependency. So let's look at this timeline. So suppose this is the timeline of a node. And if we are working in a graph events, a batch of graph events starting from here to here, then since we are working, since our task is edge class, a link prediction task, we actually cannot have the node memory includes the information in this batch, because otherwise the link that we want to predict is already in the node memory. So this causes information leak and makes your training useless. So what we do is that we catch the node memory and the node the message from the previous mini batch, and then we use at the current mini batch, we use the node memory of the previous mini batch and the current message to update the node memory to here. So the reason we need to update it to here is because we need to have this GRU update process in the forward propagation so that the GRU component can receive proper gradient in the backward propagation process. So this actually causes two types of inaccuracy or the missing information. So the first type is the stallness. So it is this yellow part due to the node memory not up to date. And the second is this green part, which we call the missing information. So this is because the node memory is not updated frequently. And what makes things worse is that if you want to scale to very large graph and you use more GPUs, for example, you use 2 GPUs than 1 GPUs, the straightforward way is to have this global mini batch and cut that to each local mini batches and assign each local mini batch to each GPU. So in order to saturate your GPU and make your multi-GPU training more efficient, you will have to make your global batch size larger. And if you make your global batch size larger, then you will have more stallness and more missing information. So in conclusion, this mini batch parallelism. So this is we call this straightforward type of parallelism the mini batch parallelism. So this mini batch parallelism training is pretty slow, unscalable, and inaccurate. So by means of slow, it is around 10 to 100 times slower than static GNN training. And it takes more than 10 hours on a billion scale graph with 8 V100 GPUs. Well, I mean, honestly speaking, this slow is mostly because the implementation or the system is not optimized. So the mini batch parallelism algorithm itself could be implemented in high training throughput. So this slow is really, to be honest, not really an issue with the mini batch parallelism, but more an issue of the existing implementation. And by unscalable, you only achieve around 2 to 3 times speed up using 8 GPUs. So this is partially because the implementation and also partially because there are some like dependencies in the node memory that you need to handle. And handling that dependencies in the node, by dependency, I mean read and write operations to the node memory. So that is pretty time consuming. And also a large problem of this mini batch parallelism is that it cannot support distributed system, which means that so this means this is because all the trainers needs to access a unified version of the node memory, and it's pretty hard to distribute them to multiple machines. And lastly, the major issue of this node mini batch parallelism is the inaccuracy. So you start to observe accuracy drops after 10 to the power of 3 to 10 to the power of 5 edges. And this depends on the data set, but typically is not large enough to fully leverage the data parallelism provided by a distributed GPU cluster. So more specifically, there are two main challenges in the scalable memory-based TGN training. So the first one is that the more GPU you use, the larger global batch size you will have. And then you can see your test F1 just drops. And if your test F1 if your accuracy of the model on trained by a distributed cluster is way lower than your single GPU version, then like no matter how fast you can train it, it's still not practical. And secondly, the issue is that all the trainers, they need to access a unified version of the node memory. So this creates enormous overheads in distributed systems. So in fact, if we just randomly split the node memory into multiple machines and have all the traffic to the node memory be remote, then using 2 nodes, the time that you spend in the node memory traffic itself is like more than 20 seconds per epoch. And this time is way more than the training time of a single node. So you won't get any speed up improvement if you scale that to multiple GPUs. So in order to solve these problems, I think our solution towards these scalable memory-based TGNs is first, you need to have a capable model. And secondly, you need to have an efficient training algorithm. And lastly, you need to have an optimized system. So more specifically in these 3 points, so for capable model, our solution is to enhance the TGNs with the additional static node memory. For efficient algorithm, we propose 2 novel parallelization strategies, and also we provide heuristic guidelines. And lastly, for mini batch system, we propose this memory daemon process, which achieves 0 overheads mini batch generation. And all these 3 improvements contributes to DistTGL, which is a scalable distributed memory-based TGN training solution. So before I move on, are there any questions? Okay, so I'm going to first introduce this capable model part. So for capable model, we propose this static node memory enhancement. So the question we want to ask here is that what should the node memory contain? So if we categorize the information in a node memory into 2 parts, the static information, which are properties that do not change with time, and also dynamic information, which are the properties that change with time. If we categorize that into two different types, we can see that the GRU node memory trained in a batch is actually pretty hard to capture the static information. So one reason is due to the nature of the GRU, which is only good at capturing the revolving trends. And another reason is that, for example, it's due to the batch training. For example, you have a node and have the burst have a burst interactions with other in a very short period of time. It is very likely that in batch training, all these interactions are combined into one and used to update the GRU cell. So this high frequency information might be important, but you only update your node memory once. So this static information is pretty hard to capture. So in order to enhance the capability of the temporal GNs to capture the static information in the node memory, we propose to use an additional static node memory, and the current GRU cell is only responsible for the dynamic information. So it can be anything that's as long as it's static, or even it is not static, but it can be written in a function of time that is even static node memory can also be that. So some examples here are static node features, learn node embedding table, and node embedding generated by static GNs. So in this work, we choose the node features if present, or the learn node embedding table as the static node memory. So the learn node embedding table is pre-trained using static GN, which don't have any scalability issue on large graphs and can be quickly trained. So
Sorry, can I ask a question?
Yes.
Hi. So this static node memory, is not going to work with new nodes, right? The learn node embedding or the node embeddings generated by static GNN.
Yes. So it depends on how you implement it. So if you use the pre-trained embedding table, yes, it's hard to apply to new nodes. But if you use node embeddings generated by a pre-trained static GNs, then for a new node, as long as it have interactions with others, you should be able to get this static node memory.
Okay, so you fix the GNN and then you rerun it when a new node appears?
Yes.
Okay, thanks.
Yeah, so this static node memory enhancement looks like a pretty simple and straightforward thing, but it actually brought a very significant benefit to the training. So for example, on the flight dataset, we can see that the dotted line are the training. So the dotted line are the validation MRR on a single GPU, and the solid line are the validation MRR on also on a single GPU, but with static node memory. And we can see that it drastically increased the accuracy and training stability. And on the right figure, we show the validation MRR of the model with static memory and without static memory on 1, 2, 4, and 8 GPUs. We can see that if you don't use static memory, you hardly can't observe any speed up in the convergence. But if you use the static node memory, look at the solid lines, clearly there are some speed up in the convergence. And this is because this static node memory, so the training of this on this static node memory is irrelevant to the batch size. And no matter how large your batch size is, the information contained in this static memory remains the same, and you don't lose additional information due to the large batch size. So these are the two benefits of adding this additional static node memory. So since its benefits not only to distributed training, but also single GPU training. So in the rest of this work, we just apply static node memory to both our method and as well as the baselines. And then I'm going to talk about the efficient training algorithm, and I will start with the epoch parallelism strategy. So the intuition behind the epoch parallelism is that we want to train different epochs in parallel using a shared copy of node memory. So if we have 4 GPU, then GPU 0 would work on epoch 0. And at the meantime, GPU 1 work on 1, and 2 work on 2, 3 work on 3. But they are all using a shared copy of the node memory. And it's you need to use different negative edges on different GPUs. Otherwise, we observe that the gradient estimation is biased and the convergence is not very good. So one question you might want to ask here is that, like instead of using different negative edges on different GPUs in this epoch parallelism, simple and straightforward strategy would be that on 4 GPUs you use the same positive batch, the same positive edges, but different negative edges. So we also test that, but it's very hard to achieve the near close to linear speed up in the convergence time. So in other words, having all the GPUs working on the same positive edges, but different different negative edges in the same iteration is not a very good strategy, because the convergence rate is severely affected. And lastly, because multiple GPUs are using a shared copy of the node memory, we only one GPU needs to update the node memory at each iteration. So for example, in this left figure, GPU 0 starts working on epoch 0 and at iteration 1. And GPU 1 starts working on mini batch 1 at iteration 1, and GPU 2 starts working at mini batch 1 of the second epoch at iteration 2. So we GPU 2 doesn't start at iteration 1 is that we want to avoid the issue that we have two same positive batches of positive edges in the same iteration. So that's effective. That's in the distributed data parallelism. That is exactly the same as you increase the learning rates. And this is something we don't want. So in the first iteration of GPU 1, we first prepare one batch of positive edges and 4 batches of negative edges. And we have to slice the node features of all these 5 batches of edges, is because that if we slice it later, then it will be updated by later batches. So after we do that, we run a forward and backward propagation. So we consume one positive batch and one negative batch. And then this green underline means that it will write back to the node memory, so that at iteration 2, GPU 1 can continue working on batch 2. And then it passes through the remaining 3 negative batches of edges and 1 positive batches of edges to the second GPU. And the GPU here just work on the second batch of the negative edge, but here it don't need to write back to the node memory. And after GPU 2 finish, iteration 2, it passed the remaining to GPU 3 and 4. So similarly, for GPU 1, starting at iteration 2, it needs to first get one positive edge back, one batch of positive edges and 3 batch of negative batches, and do the same thing. So we can see that here we have a lot of data transfer between the GPUs. So we can actually adjust the order to reduce this cross-process communication. So GPU 1 can just focus on this mini batch 1 for 4 epochs and for 4 iterations, and GPU 2 starts working on mini batch 2 at iteration 2, but also do it for 4 iterations, and so on for GPU 3 and 4. So this epoch parallelism compared with the mini batch parallelism, the benefit is that it eliminates the extra information loss in the node memory due to the larger global batch size. And the node memory always keep the same batch size as keep the same information as the same batch size if you train on one GPU. So the second parallelization strategy is the memory parallelism. So this is actually very yes.
Just a quick question, just a quick clarification. So are you still training with one negative edge per positive edge?
Yes, correct.
But you said you sample 4 different batches of negative edge for each of the GPU?
No. So so in the left figure, only the first GPU samples 4 negative batches. And the reason we sample 4 is that we will have 4 GPUs working on mini batch 1 in iteration 1 to 4.
Oh,
and
the four different batches, negative edges are for 4 different epochs. I see. Okay.
Yes.
Okay, got it. Thanks.
Okay,
I
so
also have a quick question. Just wondering, I think it's very, very smart idea. Just wondering whether basically you're changing a little bit the order of data that the model sees, right? So
yes.
at the start, it will see twice batch 1, right? So the models will get updated twice on the same data. I'm just wondering if you thought about whether this can, if you've seen whether this influences the training model.
Yes, it is.
Training.
So yes, you're actually increasing additional bias in the SGD process. Yeah, so we'll cover that, but just experimentally, not theoretically.
Okay, thank you.
Yeah,
but yeah, I think I like this idea a lot. Very, very smart.
Yeah, thank you. So another training parallelization strategy is the memory parallelism. So this is a very classic space-time trade-off. So we simply maintain multiple copies of the node memory at different time, and this mini batch in different time durations, so that this mini batches in different time durations can be trained in parallels. So for n GPUs, we simply divide the m mini batches into n chunks according to time, and we on each GPU or each trainer process, we maintain 1 copy of the node memory, and that node memory is only responsible for the event that happens in that chunk, and then we can train these n chunks in parallel. So for example, if our training dataset in total have 8 mini batches, and we have 4 GPUs, so we first split it into 4 chunks. Each chunks would have 2 mini batches, and GPU 1 would only be responsible to train mini batch 1 and 2, GPU 2 for the second chunk, mini batch 3 and 4, and so on. But there is a problem that at the end, after the GPUs finish their chunk, the node memory of on the first trainer process or GPU 1 needs to be transferred to the second trainer or GPU 2, so that the node memory of this mini batch 3 can start using the updated node memory after mini batch 2. So if your graph is large and you have a lot of nodes, then the transfer of the node memory can take a long time. So fortunately, we can also adjust the order to reduce this cross-process memory sink. So GPU 1 will work on mini batch 1, 2, and then it takes over the second chunk, work on 3, 4, so that we don't need to forward the node memory of all the nodes from GPU 1 and 2. And similarly for GPU 2, 3, and 4. So compared with the epoch parallelism, memory parallelism also don't have the issue of larger batch size leading to more information loss. But it have an additional benefit that the gather gradient from the workers are not overlapped in consecutive iterations, which give you a better estimation of the total loss. So in summary, here is a table that summarizes the pros and cons of 3 different parallelization strategies: the straightforward mini batch parallelism, the epoch parallelism, and the memory parallelism. For the captured dependency, both epoch parallelism and memory parallelism doesn't suffer from the additional information loss due to larger global batch size. And for the training overhead, for epoch parallelism, you actually need to sample n negative batches, and the bottleneck here, the bottleneck in distributed training are actually the mini batch generation. So this training overhead, or more specifically mini batch generation overhead, is larger on the epoch parallelism. And for the main memory requirement, only that the memory parallelism needs more than one copies of the node memory. So this is n time as a single GPU, but mini batch and epoch parallelism only needs to have one copy of the node memory. And for the synchronization across the trainers, the memory parallelism doesn't need to care about any synchronization on the node memory. That is because each trainer have its independent node memory, so it has advantages here. And lastly, the gradient descent variance, the epoch parallelism would give you a worse estimation of the gradient.
Can I ask a quick question on the previous slide? Or sorry, I'm not sure if you're done with this one. But if you take like the left table on GPU 4, let's say, you start from batch 7. So you have a memory specific for this chunk, as you were saying. But does your memory incorporate like what happened in the graph up to batch 7, or does it start blank from there?
Yeah, that's a very good question. So there is a small overhead. So you can either assume so in the real world, you can for the beginning, for the startup process, you can either start with all zero memory, or you can wait a couple of batches. So typically you will need to train a large number of epochs. So this overhead shouldn't be a very big issue. And also, if your data set is really, really large and you don't need to train, say, like 50, 100 epochs, you just need maybe 1-2 epochs, then I think you can start with a straight zero node memory. And in one chunk, you should be enough to get the node memory, the necessary information that is needed, because your data set is already pretty large. Yeah, that's a very good question.
Sense.
Yeah.
Thanks.
Okay, so here we know the pros and cons of each parallelization strategy. So the problem becomes like, how do you design your training configuration to like balance off these disadvantages of these models? So here we provide some heuristic guidelines for the optimized training, to achieve the optimized training configuration for this DistTGL user. And the goal, as I said, is to combine these 3 parallel training strategies to pick their advantages and offset their disadvantages. So consider that we have P machines and Q GPUs per machine. And we let I be how many GPUs to compute memory, compute one mini batch, which is the mini batch parallelism, and J be how many epochs to train in parallel, which is the epoch parallelism, and K be how many copies of node memory do we maintain, or how many chunks do we divide. That is a memory parallelism. Then we will have the following constraints. So firstly, I times J times K needs to be equal to P times Q. So this is to make sure that you have enough trainer process or trainer GPUs for each trainer. I mean, enough GPUs for each trainer. And then you need to have K greater or equal than P, since only this memory parallelism doesn't create extra overhead across a machine. And as we see before, if you sync the node memory across a machine, then the whole whole idea of distributed training is not worse. And lastly, your main memory of each machine should be hold K divided by P copies of node memory. So this is to make sure that the copies of the node memory can be stored in the main memory on each machine. So the heuristic guidelines are as follows. So we first select the largest I for the mini batch parallelism before the GPU saturates. And we observed that higher degree nodes are the major victims when I is large. So depending on the task's requirement, the user can set a threshold that like the top X% of the active nodes cannot lose Y% of information in the node memory. So this actually provides an upper bound on the batch size, which allow you to choose the largest I based on this upper bound and also your GPU capability. And secondly, we select the largest possible K based on the size of the main memory. So that is like that is because the gradient estimation of memory parallelism is better than the epoch parallelism. So we always want to use memory parallelism than epoch parallelism as long as it can be held in the main memory. And lastly, we can fix the J by P times Q divided by I times K. For example, we have 4 machines and 8 GPUs per machine. Then the largest batch size is, and the largest batch size, local batch size is 3200. I mean, the global batch size is 3200, and your GPU saturates at 1600 batch size. So then you first know that I is 3200 divided by 1600 is 2. And then your main memory can hold 2 copies. So your K is 32 divided by 2 equals to 8. So this is more than 4 machines, so you are good. And lastly, J is fixed to 2. So in this setup, we have I times J, K times J equals to 2 times 8 times 2. So before I move on, are there any questions? Okay. So last part of this DistTGL is the optimized system. So here we first have a look at the right figure. So this is a simplified task dependency graph on a single GPU. And I only show the read after write hazard. And for the previous mini batch, you need to first update the GRU memory and then write the updated memory back. And then you can slide the input of the node memory of the current mini batch and copy it to CUDA and then do the same thing. So this series of memory operations on the right critical path can actually be represented as a multi-spin lock on multiple GPUs. So here, since this memory parallelism use independent node memories, we only consider case of mini batch and epoch parallelism. So suppose we have I times J equals to 2 times 2. So 2 mini batch parallelism and 2 epoch parallelism. Then the memory access sequence on these 4 trainers are like for the first 2 trainers you read. So RI denotes the read to the node memory from the trainer I, while WI denotes the write to the node memory from trainer I. So firstly, you need to serve the read request of the trainer 0 and 1. And then after they are done, you need to serve the write request. And before the write request, and after you serve the write request of trainer 0 and 1, you can work on the read request of trainer 2 and 3. So this is like a multi-spin lock, and there's no dependency within the bracket. So you can serve the write request for trainer 1 before trainer 0. So that is totally okay. So the problem here is that if each trainer is responsible for its own read and write, then we need to have this expensive multi-spin lock on each trainers and synchronize them. So this is pretty inefficient. So instead, what we do is that we actually serialize this request to an additional memory daemon process. So the memory daemon process acts like this. So it's an additional process that we invoke for each group of node memory. And we first allocate some cross-process shared buffers so that the trainer process can communicate with the memory daemon process efficiently. So we have the read status, which stores the status of the current read, and the memory read buffer, and the mail read buffer, and the read indices. So the read indices is the indices of the read request, and these two buffers hold the result of the read request. And the write indices, the write status is the status of the current write, and two buffers are the payload to write, and these indices buffer are the indices of these payloads. So we look at an example when I times j equals to 2 times 2. So at the beginning, all trainers are just working on their own stuff. So we don't have any requests. So the demo process is waiting, and the read status and the write status of the 4 trainers are all 0. So note that in the write, like pseudocode, we start from the write, and that is because the first read in the epoch is always going to be 0. So you actually don't need to perform that read. But let's assume we start in the middle, and they are already working on something, and we start with a read request. So now at the current time, the first trainer issue a read request. What it do is that it put the read status to 1 in its own position, and then put the indices to read in the buffer array. And then the demo will see that the read state is 0 in this for loop, so that it will start to serve the read request of from the trainer 0. And then at the meantime, trainer 1 also issue a read request, so the read status of trainer 1 also changes to 1. And then in the next time frame, the demo process is serving R0 and R1 in parallel, while trainer 0 and 1 are waiting for the request. And that in the next stage, the demo process finished the read request R0, so it puts the result to the buffer arrays and set the read status to 0. And the trainer 1 see that the read request is finished, then he can start working on start training his own epoch. And then in the next time frame, this trainer 0 is really fast, and it finish is the GRU status, and you want to write back, so it issue this write request, and the write status is 1. And at the meantime, the trainer 2 issue the read request for the next group of mini batch parallelism. So so here we have the write status of trainer 0 to be 1, and the read status of trainer 2 to be 1. Trainer 3 to be 1. And the demo process here can only serve the R1 because the multi-spin lock requires that you first finish the read request from R0 and R1 before you move on. So in the next time frame, the demo process finish this a small section in this spin lock by finishing the read request R0 and R1. So it makes sure the R0 and R1 are done before moving to the next one. And at the meantime, we receive the read request for trainer 3, and trainer 2 is still waiting. So then it moves to the next section of this multi-spin lock, to the right part. So it see the write status of W0 and W1 are both issued, so it can serve them in parallel, but the read request of trainer 2 and 3 have to be served after the 2 write request is served. So after we serve these 2 write requests, we make sure they are all done, and then we can serve the read request in R2 and R3 in parallel. Yeah, so this is basically the memory demo process. But our optimized system design in this TGL have some more like engineering details. For example, you need to have separate threads to read these sampled positive and sampled negative nodes. So in this TGL, we pre-sample these positive edges and multiple sets of the negative edges and store them to disk, so that during the training, we only need to load them from disk in multiple threads. And yeah, there are some like engineering optimizations available in DistTGL, and please refer to our paper as well as the open source code for more details. So lastly is the experiment. So we evaluate using the links prediction dataset. So we have 4 small-scale datasets and 1 large-scale dataset. And we use the G4DN.battle instances with 8 NVIDIA T4 GPUs. And at max, we use 4 machines, so in total of 32 GPUs. And we evaluate using the MR over 50 candidate destination nodes. And the local batch size is chosen to be 600 edges for small-scale dataset and 3,200 edges for the large-scale dataset. And to make it a fair comparison, our learning rate is linear with 0.001 per 600 global batch size. And the negative samples in the training, we fix it to be 1. And lastly, for validation and test on large-scale datasets, since we don't have an optimizer way to test that, we simply randomly sample a 1,000 consecutive mini-batch sequence and start with all 0 memory. And all the results shown are the convergence with respect to the global epochs, which are the traversed training iterations. So first, on the top figure, we can see the epoch parallelism. So the red solid line are 1 GPU, blue are 2, green are 4, and yellow are 8. And the numbers in the brackets within the brackets are the test accuracy, and the numbers on the figure are the validation accuracy. So for the epoch parallelism, we can see that it performed pretty good up to 4 GPUs, although on the flight data set, 4 GPU doesn't have a significant improvement over 2 GPUs. But for 8 GPUs, mostly we don't observe any speed up in the convergence or only slight speed up. And also we can see that the accuracy drops as you increase the number of trainers. So on Wikipedia dataset, we drop from 0.835 to 0.812. This is because your gradient, mainly because your gradient estimation is pretty bad. And then on the bottom figure, we fix the number of trainers to 8, and we vary the balance between the epoch parallelism and memory parallelism from all epoch parallelism 1 by 8 by 1 to all memory parallelism 1 by 1 by 8. And we can see that the convergence curve, the best accuracy of the memory parallelism 1 by 1 by 8 is going to be better than the epoch parallelism 1 by 8 by 1. And the test accuracy of memory parallelism in 8 trainers is almost the same as your single GPU baseline. So here we verify the conclusion that memory parallelism perform better than epoch parallelism. And also by using memory parallelism, you can achieve near linear speed up in convergence with comparable accuracies on 8 GPUs. And on the large data set, we actually observe this like super linear speed up using a combination of mini batch and memory parallelism. And we believe that this is because the estimation of the gradient using a larger batch size is more accurate. And this is some like surprising result that we didn't expect it. But yeah, so this is the GDOT result on 1 machine, 1 GPU, 1 machine, 2 machine, and 4 machine using a combination of mini batch and memory parallelism. We also measure the training throughput. So on the Wikipedia dataset for on all the datasets for 4 by 8 GPUs in 32 GPUs in total, we achieve around 24 times speed up, 23 to 26 to 27 times speed up in the training throughput compared to a single GPU. And if we have a look at the throughput per GPU, we can see that this is a TGN baseline, and the second one is the TGL implementation of TGN. We can see that in TGL multi-GPU training throughput is not very scalable. Your throughput drops almost per GPU throughput drops almost 3 times, scaling to 8 GPUs. But on this TGL, because our optimized system design, that's not happening. And for the best, so these bars with a red line means they are the best optimization under that hardware configuration. And we can see that we almost achieve similar throughput per GPU compared to the single GPU version. So if we combine this with the convergence result, we can conclude that this TGL is a scalable memory-based TGN solution, and it's the first solution for distributed GPU clusters for memory-based temporal GN training, and it achieves negligible accuracy loss, scaling up to 32 GPUs, and near linear speedup in convergence up to 32 GPUs, and more than 10 times improvements over state-of-the-art method. So the codes of this TGL is available here, and also the paper is on the archive, and also a short promo on our recent work, Taser temporal adaptive sampling for fast and accurate dynamic graph representation learning. So this will appear in IPTPS 24, and it provides adaptive sampling for temporal GNs, and we also have a pure GPU sampler and a pure GPU cache to speed up the temporal GN training. So if you're interested, you can have a look at the IPTPS when the papers are out. So yes, thank you very much for the time, and I should leave some time for questions, but we still have 7 minutes.
Yeah, so thanks so much for the very interesting talk and like very impressive speed improvement. And I think it's really tackling one of the core issues of temporal graph, where it's very difficult to train on very large data set. And yeah, so we're still kind of like exploring the ways to training and also for evaluation and how to do that correctly. But I think with like with what you've shown here, it's like really promising to think about. You can scale this now to very, very large graphs. So I have some questions as I was listening to the talk. So I'm not the expert on the software engineering and the data parallelism, but have you thought about how do you extend this to other temporal graph models? Because I think many of the concepts are not just tied to TGN, right? Because you can take many other models that also have temporal dependency, and the way you do the parallelism, it would make sense for them as well. As long as they are using information from the previous time, they need to do kind of this kind of parallel training. So have you thought about that? And yeah.
Yeah, I think there are some like non-GN methods or even like non-machine learning method that might also benefit from this approach. But I haven't had time to be honest, I haven't had time to explore them. Yeah, so optimizing GNs are a little different to them. I can imagine that the system-wise optimization would be very hard to transfer to them, but the software part, the training algorithm part, yes, I agree. There should be some value in applying that to other algorithms.
Yeah, and looking forward to your like recent work. Once that's ready, we can invite you back again for a different talk, maybe like later in the year once that's ready.
Yeah.
And so yeah, so sounds good. And thanks for sharing the library. And I guess you will be the main maintainer of the library.
Yeah, so if you have an issue, I'm a little busy in searching the job recently, so I might not be able to answer the issue, but I'll try my best.
Yeah, okay, sounds good. So so if like anyone have question about how to use it, then they can also just post an issue on there or something like that.
Yeah, you can also ping me on Slack, yes.
Okay, great. Thanks so much. Is there any question from the audience? Okay, sounds good. And thanks for the very interesting talk. So we will stop the recording here, and yeah, see you guys next week for the talk. And thanks so much for sharing your paper.
Thank you. Bye-bye, everyone.
Nice one. Bye.